In engineering, we come across a variety of different transforms which we use to solve different kinds of problems. In this video, we will try to discuss some of the important transforms that we encounter in the field of electrical engineering in particular. And what we will try to do is to establish the relationship between these transforms. Many of these transforms are linked with each other in the sense that some transforms are special cases of some other transform. So we will try to have a brief overview of all the different types of transforms that we most commonly use in electrical engineering and see what is the relationship between those transforms so that we can have a clear understanding of how these transforms are related to each other and how they are applied to solve or simplify various problems in engineering. So to begin with, we will see what is the Laplace transform, and then we will see that the Fourier transform is a special case of the Laplace transform. And then we'll also see that Z-transform, which is another common transform that we come across in electrical engineering, is also related to the Laplace transform in some way. And then we'll find that the discrete time Fourier transform DTFT is in fact a special case of the Z transform, and we can obtain the DFT or discrete Fourier transform from the discrete time Fourier transform, that is DTFT. And then we'll also talk about the fast Fourier transform, which is not a transform in itself, but it's actually an efficient algorithm to implement the DFT. So we will try to discuss briefly what are all these transforms, and we'll try to also show the link or the relationship between these transforms and how one transform becomes a special case of some other transform. However, I will leave the applications of each of these transforms to a separate video. So the focus of this video will simply be an overview of each of these transforms and the relationship between them. So let's begin with the Laplace transform. What is the Laplace transform? It is a transform that transforms a function of time, f of t, which is a function of a real variable time, into some other function, f of s, where s is a complex variable. So the mathematical relationship to compute the Laplace transform is given by this expression. Again, we can have this Laplace transform as single-sided or two-sided Laplace transform. So you can see from the limits of the integration. So if you have it only on the positive side of the time, we call it as the single-sided or unilateral Laplace transform. And if it covers the entire time from negative infinity to positive infinity, we call it as the bilateral Laplace transform. Again, throughout the course of this video, I will be using the single-sided and two-sided transforms interchangeably, depending on the situation. But the arguments remain the same and the relationships will remain the same, irrespective of whether we are talking about unilateral or bilateral transforms. So in the Laplace transform, the Laplace variable s is a complex variable which has a real part and an imaginary part. So the Laplace transform provides a mapping of the function of some real variable into the complex variable space. So we have what is called as the S-plane. So the function f of t is mapped onto the S-plane, where the x-axis is the real part of the variable s, and the y-axis is the imaginary axis, which is the j omega axis corresponding to the j omega of the variable s. Now, if we want to check what is the relationship between the Laplace transform and Fourier transform, you can see that the Fourier transform is a special case of the Laplace transform, which we can obtain by restricting the Laplace variable s to be purely imaginary. So that means by computing the Laplace transform on the y-axis, the j omega axis, it will give us the Fourier transform. So when we force the variable s, the complex variable s, to be purely imaginary, that is, we make the real part sigma to be 0, that means we will be computing the Laplace transform along the j omega axis, and that will give us the equation for the Fourier transform. So basically what we see here is that the Fourier transform is a special case of the Laplace transform that we get when we restrict the variable s to be purely, or when we restrict the real part of the variable s to be 0. So that is basically we are computing the Laplace transform along the j omega axis, and that will give us the Fourier transform of the function f of t. So clearly we can establish that the expression for the Fourier transform, which is given by this integral, is obtained by replacing s equal to j omega in the Laplace transform integral. So Fourier transform happens to be the special case of the Laplace transform, where when we take the Laplace transform along the j omega axis, we get the Fourier transform. Next, we will talk about the Z-transform, and we will see that the Z-transform is basically the Laplace transform of a discretized signal. So if we take a continuous signal, continuous function of time, and take its Laplace transform, we get the Laplace transform. But if that continuous signal is sampled at uniform intervals, and then we take the Laplace transform of the sample signal, that would give us the Z transform. So to prove that fact, what we are going to do is we are going to take a signal x of t and then sample it at uniform intervals nt, so that we get each sample x of n as x of nt, where t is the spacing between the samples, and n is going to be some integer. So our samples x of 1 will be the value at x of 1t, x of 2 will be x of 2t, and so on. So we have these samples taken at uniform intervals spaced t seconds apart, and once we have the sample signal, we can represent the entire sample signal as, say, xq of t, which is nothing but all the samples put together. So each sample is basically a delta function, an impulse of that height, which is equal to the value of the sample. So x of n delta t minus nt. And we have all the samples put together in this summation. Now, if we take the Laplace transform of this sample signal, we can call that as xq of s, which is the Laplace transform of xq of t. And by using the general form of the Laplace transform integral, again here, I've used the one-sided Laplace transform. And after some calculation, we can get the final expression as this. Again, basically this last step here, this final integral over here happens to be simplified to this, because it's basically the Laplace transform of a shifted delta function. So the Laplace transform of a shifted delta is given by e power minus tau s, where the shift is tau. So instead of tau, we have nt here. So we get e power minus nts. So that's basically the Laplace transform of this particular function delta of t minus nt. So we have the Laplace transform of the sample signal xq of t obtained in this form, and then e power ts is defined to be equal to z, and then we will have the value, the summation converting to the Z transform. So when we define Z as e power ts, then e power ts becomes Z, and we end up getting the expression for the Z transform, which in this case is the one-sided Z transform, or the unilateral Z transform denoted as x of z. So x of z is this summation x of n z power minus n. So basically what we see here is that the Laplace transform xq of s of the sample signal xq of t is equal to the Z transform evaluated at z equal to e power ts. Or conversely, the Z transform is nothing but the Laplace transform of the discretized signal x of t. So after discretizing the signal x of t, we get its discrete equivalent, which we can call as xq of t. And then when we take the Laplace transform, that will give us the Z transform. So the Laplace transform is basically the Z transform evaluated at z equal to e power ts. Or conversely, as we said earlier, the Z transform is the Laplace transform of the discrete version of the signal x of t. So this is the relationship between the Laplace transform and Z transform. So we see that all these transforms are very closely related. And in general, for the Z transform, the variable Z is a complex number defined as R e power j omega, where R is the magnitude of Z and omega is the phase of Z. So we will now see how the mapping of the Laplace domain to the Z domain takes place. So earlier we had seen that when we force the Laplace transform to lie along the j omega axis, we get the Fourier transform. Now Z transform is nothing but having the Laplace domain transform to the Z domain such that the y-axis, which is the j omega axis, is folded into a circle encompassing all the left side of the S-plane into that circle of a radius 1. So we call this circle as a unit circle, which is nothing but this j omega axis, which has got folded cover and encompassing all the left hand side of the S-plane and converted to a circle of unit radius. And that brings us to the Z domain. So the mapping from the S domain to the Z domain is happening by converting the j omega axis into the circle of unit radius. The entire left half of the S-plane is mapped to the inside of this unit circle, and the entire right hand side of the S domain is mapped to the outside of the unit circle. So we see the relationship between the Laplace transform and the Z transform, where we see that the how the axis and the regions in the S domain are being transformed into other regions in the Z domain. So the Z transform will map an input sequence x of n into the Z domain, which can cover any point, any region within the Z domain. Now, when we force the Z transform to lie exactly on the unit circle, we will get the discrete time Fourier transform. So we see that the discrete time Fourier transform is a special case of the Z transform were obtained by restricting Z to lie on the unit circle. That is, when we compute the Z transform by enforcing that the Z transform lies on the unit circle, we will get the discrete time Fourier transform, or DTFT. So the general form of the Z transform is given by this expression where the Z is equal to R e power j omega. Now when we force this R value to be equal to 1, we will get the expression for x of z as x of e power j omega, because R is equal to 1 now, and that will now become this summation x of n e power minus j omega n, which is nothing but the expression for the DTFT, which is the DTFT, which is the discrete time Fourier transform of the sequence x of n. So we see that by restricting the value of R in the Z transform to be equal to 1, the Z transform expression reduces to the DTFT expression. So clearly we see that the DTFT is basically the Z transform evaluated on the unit circle. That is, when the magnitude of Z, the complex variable Z, which is equal to R, is said to be equal to 1. So alternatively, we can think about the Z transform as the DTFT of this modified sequence x of n R power minus n. So if you look at the expression for the Z-transform and compare it with the expression for the discrete time Fourier transform, we see that the Z-transform is basically the DTFT of the modified sequence x of n r power minus n. So anything is in the summation multiplied, the sequence x of n multiplied with the e power minus j omega n gives us the DTFT. So basically the Z transform is nothing but the DTFT of the modified sequence x of n r power minus n. So we are seeing that all these transforms are related to each other, and they become, each one transform is becoming a special case of another transform. So we see that the Z transform evaluated on the unit circle gives us the discrete time Fourier transform. And the DTFT is a continuous variable of frequency, or the continuous function of frequency. So we have the DTFT related to the Z transform. That is, when we take the Z transform on the unit circle, we get the DTFT. Next, we will talk about the discrete Fourier transform, or DFT. DFT is nothing but the sampled version or discretized version of the DTFT. So the DTFT is a continuous valued function of frequency. If we sample the DTFT at uniform intervals on the frequency, then we get the discrete Fourier transform, or DFT. So basically, the DFT is nothing but samples of the DTFT, and the samples are taken only along one cycle of the DTFT, because the DTFTs may be periodic, and it may repeat over multiple integer multiples of the period, which is 2 pi. But the DFT will take the values only over one cycle of the DTFT. Now the question that arises is how many samples are taken along this one cycle of the DTFT, and that depends on the length of the input sequence x of n. So the number of samples that we take on the DTFT to obtain the DFT samples, or the DFT points, is equal to the length of the original sequence x of n for which the DFT is being computed. So for example, if we have a sequence x of n of length n, then the DFT operation will produce another sequence of the same length n. So we have the indices going from 0 to n minus 1, which gives us n samples, and the corresponding DFT points will also have n points. So the same number of n samples are taken on the DTFT to get the n DFT points. Now, how do we compute each of the DFT points, xk? And this computation is done according to this expression. So each xk is computed using this expression, because we have x of n of length n. So we have it over the summation over that length n. And what we see here is that because the DTFT has one cycle of period 2 pi, so that one cycle of period 2 pi is being divided into n samples. So we are basically taking n samples over one cycle of the DTFT. So we have this term 2 pi by n, and that leads to the kth sample xk being computed by taking the sample on the frequency point 2 pi by n times k. So what we see is that we sample the DTFT to get the DFT. And the spacing between the DFT samples, or the interval between the DFT samples, is inversely related to the spacing between the actual samples of the sequence x of n. So the time domain sequence, if it has a certain separation between the samples, then the separation in the frequency domain will be the inverse of that spacing in the time domain. And that is obvious because the time and frequency domains are inversely related. Anything that is compressed in the time domain leads to an expansion in the frequency domain and vice versa. So finally, what we notice is that the DFT is computed for input sequences x of n, which are of finite length. So that means the DFT as an algorithm can be implemented, or as a transform, can be implemented on a digital machine or a digital hardware using some algorithms. In contrast to the other types of algorithms, which can actually not be implemented on a digital machine, although we can mathematically prove them, but implementation on a digital machine is not possible if you have an input sequence or an input signal of infinite length. So therefore, DFT is the one that is actually computed when we implement these transforms on a digital machine. So the DFT, since it's computed for a finite length sequence, it can be implemented in digital hardware. And finally, the fast Fourier transform is not a different transform, but it's actually an algorithm to implement the discrete Fourier transform, or DFT. So it's an efficient algorithm which is used widely in signal processing to implement the discrete Fourier transform. So FFT is not a separate transform itself, but it's actually an algorithm to implement the DFT. And generally, when we talk about Fourier transform implementation on digital hardware, it's actually not the Fourier transform itself that is being implemented, but actually the DFT that is being implemented. And the underlying algorithm that is used for implementing the DFT is the fast Fourier transform, or FFT. So to summarize, we can see that all these transforms are related to each other. So we started off with the Laplace transform. So the Laplace transform transforms a signal or a function of a real variable into another function of a complex variable, and we get that the transformation in a complex plane. And when we force the Laplace transform to lie along the imaginary axis, which is j omega axis, we get the Fourier transform. Next, we saw that the Z-transform is nothing but the Laplace transform of a discretized version of the signal x of t. So when we discretize a signal x of t and get its discrete version or sampled version, and then compute its Z-transform, its Laplace transform, that gives us its equivalent Z-transform. So basically, Z-transform is nothing but the Laplace transform of a discretized signal sampled in an ideal way, or equivalently, we can think about the Laplace transform as the Z-transform implemented or evaluated at z equal to e power st. We then saw that restricting the Z-transform to lie on the unit circle gave us the discrete time Fourier transform. So DTFT is a special case of the Z-transform, where the Z-transform is evaluated on the unit circle, or conversely, we can think of the Z-transform as the DTFT of the modified sequence x of n r power minus n. And then the discrete Fourier transform is obtained by sampling the DTFT. So DFT is nothing but the sampled version of the DTFT. And by taking the samples of the DTFT over one cycle of the DTFT gives us the discrete Fourier transform. And the important thing we notice is that the DFT is computed for a sequence of a finite length, and therefore the DFT is the transform that can be implemented on digital hardware or digital machine. So normally in practical applications, it is actually the DFT that is implemented on digital hardware. And finally, the FFT, or fast Fourier transform, is nothing but an efficient algorithm to compute the DFT of a sequence. So we have seen the various transforms that we come across in electrical engineering and engineering in general, and we have seen how these transforms are related to each other and how each of these transforms are special cases of some other transforms. Okay, we will talk about the applications and the uses of these transforms in a separate video, because each of these transforms are used for addressing specific scenarios or to address specific problems or to simplify specific operations. So we will discuss such things in a separate video.